Hi, I'm Nicolas. I study computer science at EPITA in France, and this year I was a Google Summer of Code contributor to LLVM. And so the project I've worked on this summer was called Half Precision in LLVM libc, and that's what I'm here to present. So first of all, if you haven't heard about LLVM libc yet, it's what it sounds like, a libc that's part of the LLVM project. There are a few things to note. It's written in C++, it supports several CPU architectures, it also supports AMD and NVIDIA GPUs, and you can learn more at libc.llvm.org. Now, the C23 standard defines new _float_n types, one of which is _float16 that corresponds to the binary 16 format from IEEE 754. There's a diagram on the right. This format is also known as half precision or FP16. It most recently gained popularity with neural networks, but it has also been used in graphics for quite a while. And as C23 defines these new float-n types, it also defines new math functions accordingly. So, for example, to get the absolute value of a float, we had f_abs_f already. Now for a float 16, we have f_abs_f16. This brings us to the goal of this GSOC project, which was to implement these new C23 float16 math functions in LLVM libc. So obviously the benefit for it is that it's a step toward C23 support. And as far as I'm aware, this makes LLVM libc the first known libc to implement these new C23 math functions. So here's the work that we've done. You should know that we split math functions into two categories, basic operations and higher math functions. So we've implemented all 70 float16 basic operations that we plan to implement. These include the absolute value function, rounding functions, maximum, and many more. Here's the link to the tracking issue if you're interested in the full list. Then we've implemented 17 of the 54 planned float16 higher math functions. These include exponential functions, logarithmic functions, hyperbolic, sine and cosine, and more. We knew we couldn't implement all of them during the summer, and here's the link to the tracking issue if you're interested in the full list again. As part of the project goals, we also wanted to optimize some of the basic operations, as some of them match quite well to special hardware instructions on certain CPUs. But we didn't want to use inline assembly or target-specific intrinsics. We don't like to do that much in LLVM, so instead we wanted to use compiler built-ins. And we've managed to optimize the float16, but also the float and double variants of the following basic operations with built-ins. So a bunch of rounding instructions to round to a nearest integer, and maximum and minimum functions. Here's some example results of these optimizations. For example, if you take the CLF16 functions on a Pixel 8 phone, the first generic implementation could take up to 8.92 nanoseconds, whereas with built-in version we get only up to 0.79 nanoseconds. Then if you take the fmax f16 function on 13th gen Core i7, if you don't enable any of the optional support for float16 instructions, it could take up to 133 nanoseconds. But if you enable support for F16C, that's hardware instructions to convert from and to float16, it's down to 6.17 nanoseconds. But either way, with the built-in implementation, it's only 3.81 nanoseconds. Finally, here's a quick example of how the float16 math functions compare in latency to the float math functions. So you can see on, again, Core i7, exponential for float16 can take up to 16 nanoseconds pretty much, whereas the float one takes up to 3.18 nanoseconds. It's currently on x86. Float16 support isn't that great, really. Whereas on the Pixel phone, which has an ARM CPU with pretty much full hardware support for float16, the float16 version is actually a bit faster than the float one. Now here are the issues that we've encountered. We've encountered quite a few actually. We ran into compiler bugs, even crashes, because on the LLVM libc website we still state that we support Clang 11, and we do really use it in some of our post-merge CI, but when we give that old version of Clang some of our float16 code and ask it to compile it for ARC64, it crashes. You can see here instruction selection failed. Then on current versions of Clang, on the other hand, we got miscompilation. So if you didn't know already, if it wasn't clear enough, not all CPUs have full hardware support for Float16. Most of the x86 CPUs only have instructions to convert from and to Float16. Other CPUs don't have any special instructions for Float16 at all. And in those cases, the current versions of Clang may generate conversions that can change the result in the code. You can see here for the absolute value function, it's supposed to just set the sign bit to 0. That's what happens on the left of Clang 16. But with Clang 19 on the right, you can see it generates a call to a software conversion function. Sorry. But when you give that function a signaling nan, it turns it into a quiet nan, which isn't encoded the same way. So when you change the sign bit and convert back, you don't get the same result. We've also run into suboptimal codegen. You can argue that's not as bad. You can see on the right, Clang 18 is generating much longer and slower code than GCC does, again on x86. But even the GCC's code is not optimal actually in this case. I was talking about optimizations using compiler built-ins, but wasn't as quite straightforward as I hoped. I made this big table where I tried a bunch of built-ins, both the Float16 ones directly and the Float ones using cast from and to Float16. I tried them across all the CPU architectures, LLVM supports, and also across Clang and GCC. When you see white green check mark, it means we can actually try to use it. It seems to generate interesting code. If it's yellow red, it just generates a call to the libc function, so we can use it to implement it ourselves. If there's a problem, it crashes the compiler. So if it's a green check mark, we can try to use it, but it might turn out that it's not worth using. Sorry. So for example, FRX F16. That's actually, like the code it generates on x86 is actually slower than our current implementation of that math function in LLVM libc. Lastly, we ran into a bunch of compiler runtime issues. So some of the software conversion functions I was talking about may be missing, depending on whether you use libgcc, compilerty, depending on the target. So on our 32-bit ARM and RISC-V CI, libgcc is missing built-ins to convert from and to Float16. On compilerty, it's missing built-ins to convert from to Float16 long x86 to convert from Float16 to x86 long double and back, no matter the target. And these functions, even if they're available, they may give incorrect results. They may ignore the CPU's current running mode and only assume that default running mode is being used. So that's what happens with libgcc on 32-bit ARM. It has a separate implementation of these functions for that target only. I don't know why. Compilerty uses the same implementation on all targets, so it has that same issue on all targets, always runs to nearest ties to even. We also had a weird issue with compilerty using the wrong registers for functions that convert from and to Float16. I landed a patch to fix that in LLVM 19, but people said it causes other issues now. The funny part is it depends on which subdirectory in the LLVM project you built compilerty from. So what lessons did we learn from all these issues we ran into? Well, you can kind of see a pattern. The less hardware support we have for a new type on a certain target, the more likely we are to run into issues with that target. Because if you have full hardware support, you don't need all these software conversion functions, for example. And currently, it seems hardware vendors are mostly interested in supporting hardware for which they have hardware support. So to make it easier for us to add a new floating point types and libraries in the future, I guess we could try to do the opposite. So first, implement fully working software implementations of operations for that new type in compilers. So from the beginning, and then only then optimize for targets with hardware support by using their special hardware instructions. And so that way, libraries could use these new types from the beginning, even if the code would be slow, at least it would actually work. And so you could save libraries from tangled conditions based on the compiler version and the target it's targeting to decide whether to enable support for these new types or not. But that would probably require convincing hardware vendors to change their priorities, so I'm not sure if that's going to happen, sadly. To sum up this talk, LLVM libc is the first known libc to implement C23 Float16 math functions, but we haven't implemented all of them yet. All of them are supported on x86-64, but we've temporarily disabled some of them on AR64 and GPUs. We've temporarily disabled all of them on 32-bit ARM and on RISC-V due to major compiler runtime issues, but we're working on enabling them back. Thank you.